And the topic of today's discussion is on unlocking the full potential of your optomechanical setup with the help of digital lock-in amplifiers. So with that, let's start with optomechanics. What is optomechanics? It's a class of hybrid physical systems that consists of typically an optical cavity, which could be also a microwave cavity, and this is coupled to a nanomechanical oscillator or a mechanical oscillator that is oscillating at a certain frequency. Both of them are coupled to each other by the so-called optomechanical coupling. And you can imagine this hybrid physical systems consisting of optical, microwave, and mechanical elements. So that means that their frequency actually lie in a different spectral regime. For example, the mechanical oscillator can lie anywhere between kilohertz to gigahertz frequency. Let's say a typical mechanical oscillator would lie somewhere close to megahertz, whereas a microwave resonator would be in gigahertz, and an optical resonator would be in the optical frequencies, let's say, which is in terahertz regime. However, the control electronics for the optical systems will always be at a lower frequency, so typically between kilohertz to gigahertz. So therefore, it's very important to have control over this entire frequency range and design electronics also like that. So as I mentioned before, the building block of an optomechanical system is an electromagnetic cavity that is able to trap this electromagnetic field, and nanomechanical systems, which is oscillating periodically. Now, due to this periodic movement of this oscillator, this changes also the phase of the optical force that is imparted on the nanomechanical system. And this phase relation basically then commands whether you can cool or heat this mechanical object. The principle comes from atomic physics, and it is then used to cool down these mechanical oscillators close to its quantum ground state. And as you can see, this is a periodic motion of a cavity, which will introduce now sidebands in the measurement. And the sidebands are separated by exactly the mechanical resonance frequency from the carrier, which is the optical carrier. And these sidebands are quite important because they carry not only information about the mechanical object, but also these sidebands carry information about the quantumness of this mechanical object. And they're often termed as Stokes and anti-Stokes lines. So that brings me to the current situation on optomechanical system. For the last couple of decades, there has been a lot of research going on optomechanical system. The first decade focused on cooling them down, as I mentioned already, close to their quantum ground state. And this was achieved, as you can see in this paper, more than a decade ago with both optical and microwave optomechanical systems. The next decade followed creating some fancier quantum states from these mechanical systems, such as coherent states and squeeze states. One of such research I was also involved, as you can see here, where we were able to create a squeeze states out of a cavity optomechanical system. At the same time, there was a lot of focus on realizing room temperature quantum optomechanics. For example, a group in Vienna was able to create such quantum mechanical systems at room temperature using nanoparticle objects, while another group at EPFL were able to demonstrate room temperature quantum optomechanics with their optomechanical systems. So now the trend of this research field is evolving because creating quantum objects out of the system is kind of regular. So the research is focusing a bit more application-specific areas. For example, realizing hybrid quantum systems such that quantum states can be transferred from one physical quantum system to the other. Using them as a sensor, for example, nanomechanical systems are well established already in terms of classical sensing. But now with this quantum optomechanics principle, you are also able to build quantum sensors out of them, testing very elusive quantum gravity, because for that you need very high precision, using them as quantum memory. And that is also quite attractive because these nanomechanical systems typically have a very long coherence times, which can even last until hours. So that's why they are quite interesting as a memory device. So as you can see there, most of them are using somehow combining optical and microwave and mechanical elements at the same system. And I cannot stress it enough. This is where you need to read a wide frequency range electronics that can address and control this physics. And this is exactly where we come in, because we are helping you to choose the right instrument to make sure that your experiments run smoothly. So our instruments can go from DC to the specified bandwidth. So for example, if I look at the SHFLI, it can go from DC to this 8.5 gigahertz maximum frequency. And they are typically a lock-in amplifier, but actually they are a bit beyond that. Because one lock-in amplifier, in fact, will include an oscilloscope, spectrum analyzer, sweeper modules, imaging toolboxes, PID, PLLs, arbitrary waveform generators, and also boxcar. And the beauty of this is that you can run all these toolboxes independently and at the same time. How do we achieve this? We achieve this by actually taking off-the-shelf hardware and combining them with the software architecture that allows us efficient workflow, great functionalities and feature, intriguing UI. And this also means that we can add value over time for the customer by bringing new features to it. Currently, we have 4 pillars in our instrumentation. So it includes quantum control systems, lock-in amplifiers, boxcar averages, and impedance analyzers. Today's talk, of course, is going to focus more on lock-in amplifiers. So for the ease of discussion, I segregated this into mainly 4 parts. First, I'm going to talk about the general characterization of the resonator. I'm going to talk about spectroscopy and time domain measurement. Then I'm going to dive into a bit more advanced topics that can be done with our system. And finally, towards a little bit of perspective section, where we talk about where this optomechanics community is heading and how can we help them. So let's start with some general characterization of this resonator. So the first question is, how do we measure these systems? So the first part would be of an experiment would be to characterize your resonator. This could be a microwave resonator, an optical resonator, or a mechanical resonator. So if it's a microwave resonator, the answer is quite simple. You simply plug into one of our microwave lock-in amplifiers, and then you're able to characterize them fully. If you are using an optical system, then you typically use some kind of modulator, for example, AOM, acoustic modulators, which allows you to sweep the frequency of the laser and scan the cavity to find the cavity resonance. You can do the same thing by also using a DC offset to change the piezo that is controlling the cavity, and that's how you can scan the cavity as well. And then you can measure directly the photodiode response to the scope tool of our lock-in amplifiers. Let me show you an example. So for an example, I took a microwave 3D resonator, which is made up of aluminum. This 3D resonator actually supports many electromagnetic modes that are going from few gigahertz to several gigahertz. As you can see here, we can use the inbuilt sweeper tool in our lock-in amplifiers to sweep the excitation frequency and measure the response of the microwave resonator in transmission. And you can see that we are able to see several of these modes at the same time. So as a next step, what we do is we should focus on one of the modes. Let's say we want to look at the fundamental mode, and we want to look at very closely this mode. Why we want to do that? There are many reasons. One of the reasons could be that I want to find the resonance frequency, amplitude, but I also want to find the Q factor, for example. And this is quite important because the Q factor actually gives away the losses that are associated with such microwave resonators. And it's defined like this, simply by the ratio of the full width half maximum of the spectra and the resonance frequency. And this is quite convenient now because with the sweeper module, now I can focus on this mode, sweep for a shorter range, and you can see I can nicely find the amplitude and phase response. And with inbuilt fitting tools, I can actually fit this Lorentzian and directly find the resonance frequency, amplitudes, and Q factors directly from the Lab 1 software. If I want to also measure in temporal domain now, because maybe I want to measure in another way to get the same parameter. This is also possible because typically what you have to do in such case is what is known as ring down experiment. So the idea is that you stop pumping your cavity at a certain point, and then the photons that is inside the cavity will decay with the characteristics lifetime. This is called the decay time, tau, of this cavity. And this actually is directly related to the losses of the cavity as well. I can see this. There's a very nice formula that kind of relates the Q factor and the decay time. And you can also find the Q factor in this manner as well. So what we can do now, we can, instead of using the spectrum domain measurement, we can use the temporal domain measurement, and we can switch to the data acquisition module, where we're able to trigger such measurement. So we can see that we can set the trigger delay and the hold of time in such a way that we capture nicely this ring down. And we also have to choose, of course, the data transfer in the correct way. And once you've done that, then from this measurement, you can directly estimate also the tau, which additionally gives you the Q factor as well. Of course, it's needless to say that you can do the same thing with an optical resonator or with a mechanical resonator. So this brings me now to the advanced applications. And I'm going to focus on mainly three different type of applications. I'm going to start with what is called injection locking. And let me start with briefly explaining you what exactly it is. So injection locking is actually used in sensors, in metrological systems, and in timekeeping networks to design clocks which have a very low phase noise. In addition, you might also want to have this clock have some long time stability as well to protect them from environmental fluctuations. And this is typically achieved by injection locking on a self-sustaining oscillator, which gives you, in turn, stable frequency with a low phase noise. How can you do that? You can do that by, first of all, having a low phase noise, rather a free running oscillator with a certain phase noise, as you can see here. And the phase noise actually in this case is typically quite wide. And then injecting AC signal that is from an external circuit, which has lower phase noise. And above a certain threshold, this free running oscillator will actually lock to this injected frequency. And this is called the Adler's principle, and it follows this so-called Adler's equation. And the advantage of that is that at that regime, you get the oscillator with significantly less phase noise. So in this example, we want to study injection locking on a nano-opto electromechanical platform. And you can ask me why. In typical applications nowadays, people are using optical fibers to achieve it. And this involves actually fiber loops which can run through kilometers, actually. So that makes them not so very compact and not so very easy to use. Instead, if you can have a small chip that actually can do this job for you, then you can imagine how it is much more easier to implement it. So to do that, the first thing we need is a mechanical resonator that is working at the microwave frequencies, so gigahertz frequencies. In this way, you can directly map the microwave drive at gigahertz to this mechanical resonator. And if this mechanical resonator is also coupled to an optical network at the same time, you can in turn map this gigahertz frequency to the optical network. So at the end of it, you map the microwave domain signal directly to an optical domain signal by using the mechanical oscillator as a transducer in between. So the strategy in this case would be either to directly inject the microwave signal to your nanomechanical oscillator, or you can also use by optical means, for example, using a modulator to modulate this the optical signal, and thereby you injecting the microwave signal in the nanomechanical platform. And finally, what you have to do, you have to measure directly at the gigahertz frequencies to get the amplitude and phase. On top of that, in some applications, maybe you also want to stabilize your system over time. And this kind of long-term stability requires you to implement further feedback control on the system. So we had the privilege actually to do such measurements in the group of Remy Brough in Cédozen in Paris-Saclay. This is a group which is actually working on making such clocks. Their system consisting of gallium phosphide optomechanical crystal, as you can see here by the blue color. This is a one-dimensional optomechanical crystal. On the bottom of it, you find the gold electrodes that is allowed to also excite these mechanical systems. And also it has optical fibers that are coupled to these mechanical systems by the means of waveguides that are also placed beneath this mechanical resonator. So the excitation can work in both ways. You can excite them optically or microwave through microwave lines. But the detection is typically always with optics. So you have a photodetector that allows you to perform a transmission measurement. And remember, the photodetector converts the measurement into a rotating frame. So then what you have to do for the measurement side, you have to directly measure this nanomechanical oscillators, which are at gigahertz frequencies. So I kind of introduce now a familiar picture for you. You see that these measurements also will create typical sidebands. So the FC would be then your optical carrier and the two sidebands coming out of the mechanical coupling. However, if you're doing a homodyne measurement, which is done in this case, the sidebands actually will overlap on top of each other. And therefore, you have to measure directly at 3 gigahertz frequency, which is typically the eigenfrequency of this resonator, to measure the stability of this system. So the challenge is that, first of all, you have to track the phase of this nanomechanical system as a function of the phase of the injected AC drive. And therefore, this is a phase-sensitive measurement, and therefore a lock-in measurement is typically required. You can also track the amplitude of this mechanical oscillator as a function of time, but this is typically susceptible to amplitude noise, and that might not always give you the right picture. So now we're coming to the experimental part. So the first part of the experiment is to find out where your eigenfrequencies of these mechanical systems are located. Since we know typically this mechanical eigenfrequencies will be around 3.1 gigahertz, what we can do, we can park the center frequency of our spectrum analyzer tool in the lock-in amplifier at 3.1 gigahertz and set a sufficient bandwidth that we can capture this mechanical resonance, which is around 3.081 gigahertz. And then when you have this spectra, you can do all these nice things that you want to do. For example, find out the resonance, amplitude, Q factors, also allows you to find out optomechanical coupling. So once you've done the basic characterizations, now you want to implement this injection lock-in principle. And to do that, what you have to do is first park an AC drive close to this mechanical resonance, but outside the original mechanical resonance. And for a certain threshold of amplitude of this injected drive, this resonator actually will lock to this injected AC drive. And then when you sweep the frequency of this AC drive, you see kind of like a flat region in the amplitude response and a linear phase response as a function of this frequency sweep. And this is an indication that the two frequencies, the two oscillations are locked to each other. You can do another test by ramping up this voltage, the injected drive voltage. And you see that if you do that, you increase this locking region significantly for a higher drive. And this is a typical principle of injection locking, typical feature of this injection locking, that when you keep on increasing this drive, you keep on increasing the locking regime as well. Actually, the group published a very nice paper last year where they exhibited this principle in this very nice paper. So you can see the mechanical motion, actually, the original mechanical motion in yellow. And you can see this is quite broad. And while the injected AC drive is very narrow, and when this injected AC drive is quite close to this mechanical oscillator, you see that the mechanical oscillator actually locks to this AC drive. And you can see already here, you can already appreciate that there is a significantly low phase noise now of this mechanical oscillator. What you can do, actually, you can go further and you can do phase noise analysis. You can measure Allen variance, like it's suggested in this blog post. And that kind of allows you to access all these parameters that show you how well you improve the phase noise of the oscillator. And a lot of that is actually discussed in this paper. Great. Now I switch topics. I come to another example, and this is a very typical optomechanical systems, very pure, because it couples a microwave cavity to a nanomechanical oscillator. The measurement were also done with my colleague at the lab of Hans Hubel at Technical University of Munich. The cavity, basically, it's a superconducting cavity, which is working at gigahertz frequencies, while the mechanical resonator is working at megahertz frequencies. So you can see that they are working at two different spectral regimes. So that means that the microwave resonator has to be characterized by VNAs, spectrum analyzers at such frequencies, while the mechanical resonator has to be measured at lower frequencies. And this is typically done by using mixing techniques and down conversion, for example, IQ mixing, and which means that this is difficult to design, and also you have to be very careful while doing the calibrations. So that means the entire experimental design aspect is kind of complicated. But just imagine now, if we plug in an SHFLI directly to the systems. So there, we can actually have control over this entire frequency range, because as I mentioned here to you before, our instruments go from DC to the specified frequency. So the first thing we would do here, we would park our excitation frequency somewhere close to the cavity resonance. And then if you sweep this frequency, you'll be able to identify already the amplitude and phase response of this cavity resonator. And you can see this very nicely here. So this allows you to actually access the cavity resonances, Q factors, and all these parameters that you want to measure. And once you're done, then what you want to do is now you want to measure the mechanical oscillator. And this is, again, we're coming back to the sideband picture that I already introduced to you. So typical experiments would use a so-called homodyne technique. That means that you pump the cavity at resonance and you observe these two sidebands. Now, because the lock-ins have many oscillators and many demodulators, you can actually see the sidebands and the carriers at the same time. But this is a so-called resolved optomechanical systems. What it means is that the cavity line width is significantly lower than the mechanical oscillator frequency, which means that in transmission, the mechanical sidebands are heavily filtered out, and that makes them very difficult to see in an actual experiment. So this group devised a very clever technique to measure. What they do is that instead of driving the cavity on resonance, they drive it outside the resonance, such that one of the sidebands will fall inside the cavity resonance, and therefore you can observe this resonance very nicely in transmission. Of course, you can observe the other sidebands as well at the same time by pumping the cavity on the other side. And again, because you have several oscillators and several demodulators on the lock-in, you can do both these measurements simultaneously. Inside the lock-in, of course, you can design the filters in an even better way to filter out any other noise that is present in your measurement. And this way you can filter out all the noise that is kind of bothering you. And then voila, you see that we are able to measure this mechanical oscillation directly. Remember, this is the Brownian motion of this mechanical resonator that we're watching. So there is no drive of the mechanical oscillator that is involved. And after doing a bit of calculations, simple calculations, we can finally find the mechanical resonance frequency, which is around 5.8 megahertz. This is something which was already expected, so that only confirms the measurement. Great. Now that I'm done with this sideband picture, I want to move to the third set of experiments that I proposed to you. This is a bit more complicated than what I've already introduced to you, because it also involves many topics and measurement techniques. So first of all, let's assume that we want to measure some modulation aspect of my cavity optomechanical systems. So we can probably want to send a frequency modulated wave to my cavity, and I want to measure the reflection, which becomes amplitude modulated. And you can ask me why I want to do that, because maybe I want to implement some stabilization technique using this. So remember, our lock-ins, all of our lock-ins have inbuilt modulation channels. So you can actually send and measure frequency and amplitude modulated signals, but you can also do PID stabilization by using the inbuilt PID tools. And this is very useful for a certain technique. It's called Pound-Driver Hall technique. This is a very popular technique in any optical cavity or macro cavity related topics, because this gives you an unprecedented level of stability in your setup. So why this is quite interesting? Because the way it is implemented, it's kind of frees you from the phase noise issue of the laser or of the microwave drive that you're using. So you're not limited by the phase noise of the laser or the microwave drive at all. Rather, your cavity will determine the stability of your measurement. And as we all know, microwave cavities typically are super stable, similar to as well as optical cavities also can be super stable. So in this experiment, what you have to do, you have to send a frequency modulated signal to your cavity, which is in this case a resonator, micro superconducting resonator as well, working at 6 gigahertz. And you measure the transmission or the reflection with a power detector, which converts, again, remember that this power detector is like an optical detector, will work in the rotating frame, so thereby removing the carrier completely. Thereby, you're only left with the modulation frequency, 50 megahertz. And then you measure with the same systems that you're driving, and finally feed the measurement back to your PID unit, where you get this nice PID, this PTH rather, signal, and then you can use to close the loop. This experiment was performed in the lab of Corey McRae at CU Boulder by my colleague Jim Phillips. And in that very nice blog post that they published, they also showed that this technique also allows you to do a very fast Q factor determination using the second harmonic. So if you're interested, please go and have a look at this blog post for more details. Great. So this means that I'm done with the continuous measurement at this point, and I would like to look at a little bit of the future of optomechanics. And this brings me to some pulsed optomechanical systems that are becoming much, much more common nowadays. And my motivation is also to motivate you to show you why these systems are so interesting. So the first concept of pulsed optomechanics is not new. There was a very famous theoretical paper that was published again more than a decade ago, which talked about using pulsed optics on such optomechanical system. And the optical pulses actually had to be shorter than the mechanical oscillation time period. And this is the case because the idea was that this way you impart less intensity noise on the mechanical oscillator, which eventually prevents you cooling these mechanical oscillators towards the quantum ground state. These are so-called back-action evading measurements, with which you can actually realize squeeze states by using pulsed optomechanics. There was a lot of effort after that given to validate this experiment. For example, the group of Oscar Painter did experiments with pulsed optomechanics with such systems where they basically pulse the laser on such optomechanical platform. This is also a one-dimensional optomechanical platform to realize this experiment. And they were able to do some very nice experiment close to the quantum ground state. And nowadays, this is becoming even more common because of the nice transducer capability that the mechanical systems have. So, for example, I love this example. Actually, this is a group in Canada which basically coupled spin qubits to a mechanical system by using stress coupling. At the same time, the mechanical oscillator is also coupled to a photonic cavity. This is by the principle of optomechanics. And this way, it allows them to actually transfer information from a spin qubit system to an optical network. So this is truly a transduction scheme, which allows you to transduce quantum information from one physical system to another physical system. And it's truly an example of a quantum hybrid system. And what is even more interesting is that you see in this picture that it requires different type of pulses with different time duration, but also importantly different frequencies, because it involves optical systems, microwave pulses, and also mechanical systems. So if you see this time domain picture, you'll be able to appreciate how many different type of pulses are actually used in this experiment to realize this, which is not so straightforward, of course, because that means that you have many electronics that are in the same experiment, and you have to control them, time them, and when you're scaling up, it's become quite difficult and very challenging to implement it. The same example also works for another system, which is now using a surface acoustic wave coupled to a macro resonator through qubits. And as you can imagine, here also pulsed microwave pulses are required to couple the systems. And then again, you are also working at different frequency regimes. So just to summarize what I already discussed, so the optomechanical community is going towards pulsed measurements. And this is because, as I mentioned in my first slide, that optomechanic systems are going towards more application-driven areas. And most likely you want to couple different kind of quantum systems, qubits, to these mechanical systems. And that's where pulsed optomechanics or pulsed measurements are becoming crucial. But also, optomechanical systems are going towards higher frequencies, towards gigahertz frequencies. Why that? It's because at such frequencies, it's much easier to realize room temperature quantum mechanics with them, which makes them more efficient and also more cost-effective. But high frequencies typically will mean that you have shorter pulses. And that means that they're more difficult to design and more difficult to control. And imagine now if you have a truly hybrid quantum mechanical system, you have to have such pulses working at different frequency regimes with different durations. And the complexity, again, I cannot stress this enough, increases when you have to control all these pulses working at different frequency regimes. So now just imagine if you have one system that is able to generate pulses, which are working at different frequencies, you send it to your experiment, you measure your result with the data acquisition toolbox that is inbuilt in the same instrument, you measure all of them simultaneously, and that actually makes the measurement much more easier in terms of experiment size. So from the designing of the experiment point of view, it is much more easier. It is much efficient and effective actually to control and time your measurements as well. So coming back to this picture again. So if I have an optical system, I can do first continuous measurements, which are, of course, you have to always do, because you have to find your cavity resonances, your mechanical resonances. You have to find that doing spectral domain measurement, temporal domain measurement, and this can be all continuous measurement. But then you might want to go to a pulse measurement. And the interesting factor is that you don't have to switch instruments now. You can use the same instrument to do your pulse measurement by modulating, for example, the modulator in your optical experiment. At the same time, you can also derive your mechanics continuously if you want to, or you can do some feedback control on that to stabilize your cavity or your interferometer. The same concept also goes for a microwave optomechanical systems. Here you send pulses to your microwave optomechanical system, you measure them, and you can also do the stabilization, control, drive at the same time. And going even further and realizing now, again, as we discussed, these hybrid systems, you can imagine now maybe your mechanical system is coupled to a cavity, an optical cavity, and a microwave cavity at the same time. So the mechanical oscillator, when it oscillates, it changes the capacitance in this microwave resonator and changes somehow the cavity length. so that both frequencies are coupled to each other. And there, with such a single instrument, what you can do, on one hand, you can drive your optical measurements. You can send pulses to your optomechanical systems by optical means. At the same time, you can send microwave pulses to the same system and also measure them at the same time. And on top of that, you can do stabilization and control by the same instrument. And I'm not talking about science fiction here. There are groups which are already doing such measurements. For example, this is a group in Delft who are using such optomechanical systems, as you can see here, between optical network and a microwave resonator. And both these examples actually show how they can transfer optical pulses or optical information to microwave frequencies and truly use this resonator as quantum transducers. So the bottom line here is that with such a multi-instrument, you can control many aspects of your experiment that is working from DC to 8.5 gigahertz. So now I would like to conclude. And in the conclusion, I would like to remind you again this sideband picture, which is the most important part of such systems. And yes, that I wanted to establish during this webinar is that optomechanical systems already require complex setups and with control electronics that will spread over a huge frequency range, which makes them already very challenging, but even more because they are going towards application-driven areas. They're going towards quantum sensing applications such as quantum memory, and using them as transducer for quantum state transfers, which makes even more difficult to design such experiments because these applications will require pulsed measurements on top of continuous measurements to implement. So with that, I would like to thank you for joining this webinar, and I'm really looking forward to your questions.